For the next 30 minutes, we're going to take you on a trip to Mars and back. Good day, I'm Amika Cowder with NASA Public Affairs, and I'm joined by an expert in the field of planetary science, Jim Green, Director of NASA's Planetary Division. Also joining us is NASA astronaut Stan Love. NASA has robots and rovers on the surface of Mars and is planning on sending humans there as soon as technically possible. But there are stepping stones to getting there, conducting valuable scientific research and returning home safely. What we've learned up to this point has been invaluable in providing the initial exploration steps to one day sending astronauts to Mars, and Jim is here to discuss the next steps and help answer the questions of what a crew might experience on the Martian surface, what kind of samples could be returned that would provide scientific value, and also determine how crews could use natural resources to live off the land for short and eventual long-term stays on the red planet. And no stranger to spaceflight, astronaut Stan Love also joins us in the discussion of what it takes to live in space for what we consider long durations right now, but what will be considered short one day as human missions become longer and distance from Earth become greater. So I understand we have had a few Mars rovers out there roving the land since, back in the 1990s, correct?
Correct.
So what can you tell us? What have we learned so far?
Well, the rovers really provide invaluable information about various regions that they roam, because that's you get up close and personal. You can really look at the rock structures. You can really see much more about the mineralogy and their elemental composition, and that's incredibly important. Not only does it tell us about the history of Mars, but allows us to think about how we can use the resources that are trapped in the rocks for supporting humans as we might need to when we go there.
Great. And so for you, Stan, being an astronaut, what does this whole journey to Mars mean to you?
Well, it's the ultimate goal for human exploration. The furthest thing out that we can think of for the next 30 or 40 years. There are other destinations in the solar system that we could send people to, but most of them are even harsher and more difficult to reach than Mars. Mars is a whole world. It's as big as a major continent on Earth, and it's basically unexplored. We have photographs from orbit. We have a few kilometers worth of rover driving, but it'd be wonderful to send humans there and see what we can see with our own eyes.
So what are some of your questions for Jim Green here, being an astronaut and thinking about that harsh environment? What are things that you would have to ask him?
Well, the things that we'll have to solve before we can send people to Mars include what's the radiation environment like down on the surface. We already know what sort of temperatures we'd have to protect our people and systems against. How prevalent are the dust storms, and especially how bad is that dust to deal with on a personal level. We understand that it can have effects on solar panels, so if we're using solar power on the surface of Mars, you don't want your power station to get covered with dust and not produce power anymore. We're interested to know if the chemistry of the rocks and dust are somehow dangerous to people. We're used to living with rocks and dust here on Earth, and it's usually not a big problem. But if the chemistry on Mars is different enough, we come back into our habitat with dust all over our suits. Is that going to give people allergies or poison them? All good stuff to know. And then, of course, most of our activities on the surface of Mars are probably going to be related to geological science. When we send crews there, we will send some pilots and engineers. We're also going to send some geologists and planetary scientists, and we'll be interested to know what tasks they'll be doing down there on the surface.
We actually understand the radiation environment reasonably well, and what we find that since we've been measuring it in space, that down on the surface it's about half as much as it is in space. So the atmosphere doesn't really provide an extensive amount of protection. The reason why it's half as much is because the planet is protecting you from half of the sky. In terms of other resources, the dust is a problem, although it may not be as big a problem as we thought. Mars is very dusty through the whole planet. In fact, at some times, and there are certain seasons in particular where global dust storms may exist. But the dust actually is fairly not thick, but thin in the sense that dust storms can actually reach very high altitude and really provide an opaque view of your horizon and the sun. So they block out a lot of the light, still get into everything, and we'll have to watch how to manage and manipulate that. But it's probably not as big a problem, something that we'd be able to manage. There are regions on Mars where there might be some pretty harsh chemicals that are embedded in the soils. And so you're going to want to constantly take soil samples. Perhaps before we land in a particular area, we're going to want to return those samples, analyze them, and know exactly what we're getting into before we go there. So that would be something important. I agree with you completely. A lot of geology can be done. You know, the geology will tell us the history of Mars. We now know that Mars in its past had extensive amount of water. Perhaps oceans, certainly rivers, lakes, fast-moving water for tens of millions of years, maybe even hundreds of millions of years. And so consequently, there's a fair amount of water still left on Mars. We know that the atmosphere has changed significantly. The water is mostly evaporated, but it now looks like a lot of water is actually seeped into the ground. And so you'll have some resources available to you. You'll have water resources. You'll have a variety of minerals and maybe building materials that you can get access to. That'll be important in terms of supporting humans. The science that you'll do will be absolutely spectacular. You know, our rovers have been on Mars for many years, like Spirit and Opportunity. Spirit no longer is operating, but Opportunity still is. And Curiosity just passed its second-year anniversary. And although they've made a lot of measurements and done a lot of things and traveled many kilometers on Mars, actually humans could have done most of what they did in a much more rapid time frame. Perhaps a matter of days, if not weeks, could have collected the kind of information they are doing. But with that information, it's providing us what we call ground truth. It enables us to then use our orbital assets and say, here's what hematite looks like, here's what the clays and sulfur look like down on the ground, and here's what it looks like when we map that from space. And then we can look at the rest of the global resources that exist on Mars. Mars is truly a fantastic place. The vistas are absolutely unbelievable. There's huge canyons, you know, like Valles Marineris. If it was on the United States, Valles Marineris would stretch across the United States from one end to the other. Huge shield volcanoes, you know. Mount Olympus is as big as the state of Missouri. I mean, there's just a tremendous variation in the land and the geology, and that provides a lot of exciting opportunities for the scientists.
So a lot of really interesting things we're talking about here. First, I would like to go back to you. You talked about some of the things about getting the samples. I know we gathered a lot back in the days of the Apollo days when we had the moon rocks. What is it that you hope that we'll be bringing back and returning Mars rocks?
Well, you know, we're still actually looking at the lunar rocks. We have a variety of fabulous laboratory equipment that's been developed that allow us to really take those rocks apart and understand the early evolution and composition of the moon and the Earth. We want to do the same thing at Mars. We want to be able to obtain samples, analyze them in our laboratories. You know, we just can't build a rover big enough to be able to take the equipment that we currently have in our labs now. And that's essential if we really want to study the detailed geology and the geological history of Mars.
So, can you tell me now, what from those samples, just from the images alone, not the actual rocks, what do we know so far just from the images that we've received from Curiosity and the other rovers?
Well, what we're finding out now is Mars has some fundamental material that is incredibly important. It has, in the rocks, we find hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those are some of the basic building blocks of life. It also sees that this material was deposited over time in rapidly flowing water. And so we can tell that the water in millions and billions of years ago when it existed on Mars was actually drinkable. It wasn't salty at all. So it really looks like back in Mars's early history, based on the chemistry and based on what we're finding in the rocks, that Mars could have had a number of habitable environments in it. And perhaps life started on Mars just like it did here on Earth.
So is it safe to say that Mars is, we feel, resourceful enough for us to actually live off the land, which I'm going to turn now to Stan and ask you, now that's a long trip, how do you think that we're going to go about? What are the plans?
Well, that's two different questions. How are we going to get there for the long trip, and what could we use to live off the land? How we're going to get there is a tough problem. We would need a ship about the size of the International Space Station. And then we'd have to accelerate that clear out of the Earth's gravity well. It would have to fly through space for 9 months to arrive at Mars. And then when you get to Mars, you can't just plant the flag and come home the way we did on the Moon. The Moon is always circling the Earth, and you can come home anytime you want. If you land on Mars and then take right back off again, try to come back to the Earth, you are likely to arrive at the Earth's distance from the Sun, while the Earth is on the other side of the Sun, and then that's not so good. We never come home that way. So you're sort of committed to a stay of about 1 Earth year, or about half a Mars year, on the surface of Mars before you can come home. All told, total trip duration 30 months, so 2.5 years. Then the systems that we'll need, we're not sure how to land a 40-ton habitat on Mars. Remember, you're going to live in this thing for a year. So if you try to live in something the size of a minivan with your 3 buddies for a year, that's probably not going to work so well. Plus, you have to bring all your food, all your water, all your breathing air in case you're not able to use the resources that are there on Mars. And that adds up to a lot of weight. Right now, you can land something up to a few hundred pounds on Mars under a parachute with airbags. But if it's bigger than that, the atmosphere is too thin to provide enough deceleration with parachutes. So you have to go to a rocket stage that actually slows you down and then lands you gently on the surface. We're not sure how to do that. One of the things that the space station is teaching us is that once we've built a machine, and near and dear to the crew's heart is the life support systems, a machine that takes carbon dioxide out of the atmosphere, for instance. You're always breathing in oxygen, you're breathing out carbon dioxide. Once carbon dioxide gets up to 1% or so of the air you're breathing, or even less, it starts causing headaches, you get changes in your blood chemistry, it's not a good scene. We have those machines on the space station, and they're not as reliable as we hoped they would have been. So the crews are always having to tear them apart and put them back together again, using spare parts brought from Earth. Now, if you're on your way to Mars for 2.5 years, you have to bring all the spare parts with you or do without. So that kind of reliability is something we still need to perfect. We're not there yet. As far as living off the land, so Mars has the chemicals of life. The atmosphere is carbon and oxygen and nitrogen. That's great. Oxygen and nitrogen are what we breathe here. But Mars's atmosphere is very, very thin. It's like being at 100,000 feet altitude on the Earth, and you can't live at that altitude. They call above 26,000 feet on Earth the death zone. Once you're up there, climbers of high mountains like K2 and Mount Everest, their bodies are breaking down every minute they're above 26,000 feet. Plus the chemistry of Mars's atmosphere, we're breathing oxygen. It's a very reactive chemical. If we didn't have plants regenerating our oxygen here on Earth, in a few hundred years it would be gone completely, and the atmosphere would not support human life. Mars does not have that kind of biosphere creating oxygen that we can breathe, so its atmosphere is chemically at equilibrium with the surface. It's just carbon dioxide. We can split carbon dioxide up into carbon and oxygen and make oxygen, but that takes a lot of energy. And the machinery to do it, we're not sure we can make to be perfectly reliable. We know there's lots of water on Mars. It has polar caps made out of frozen carbon dioxide, dry ice, and water ice. And we know there's a lot of water frozen in the ground. You can dig that up and use it, but again, you need digging equipment that's going to work on Mars, essentially in a vacuum at temperatures that can go down to 100 degrees below zero at night. And you know your car doesn't like to start at 100 degrees below zero. So there's a great deal of technology that we sort of take for granted here on Earth, mining machinery, chemical processing machinery. You go up the road here, we live in Houston, see all these amazing, huge chemical plants. That kind of chemistry you can do with the infrastructure that we have here on Earth. On Mars, we'd have to bring it all with us. So the near-term missions for Mars that I've seen described are a little hesitant to use what's on Mars, not because it's not there, but because we're not sure we'll have the technology we need to use it when we get there. So we'd rather bring something with us and be absolutely sure we can get it and use it than be depending on something, get there, and find out we can't get it.
Doesn't work.
That's not so good.
No. Well,
so there
that's
you go.
Very interesting. So let's talk again now. I'm going to just throw it out there because everyone wants to know. Is there life on Mars? I mean, we say it's a living planet. Do we know? Are we hoping that maybe we'll find something? What would Stan be looking for if he's out there, if he's out to search for life on Mars?
We don't know if there's life on Mars or not. So we're actually seeking the signs of life. Life may have been in an environment in its past where it could have started and evolved over a period of time. There's certainly not complex life. There might be microbial life. And if microbial life is there, it's going to be probably under the surface. When an environment gets tough, life seems to move into the rocks. Here on Earth, planetary science has an activity of looking for life in the extremes. We go out in the driest deserts. We go down in the deepest mines. And every place we go, we do indeed find life on this planet. It's really remarkable. And so Mars may also have been an environment for which, as the climate changed, which it did at some time in its past in a significant way, losing most of its water and a lot of its atmosphere, then life could have gone underground. So that's a possible approach for us to take in the next series of missions, where we actually are then more sure that we can go to an area where there's possible conditions, habitable areas where we would look for life. But we don't know that they're there. We don't know if extant life, meaning current life, is there now. There's also potentially some past life that may be found within the rock remnants that we would want to bring back and analyze. We don't know if that's possible or not. Mm-hmm. So those are approaches. But I tell you, what's really exciting is we're really now starting on the path of looking for life at Mars, whether it's extinct or currently there, extant life. And I think we're going to find some exciting things as we move in that direction.
I actually, to be honest, I never thought that I would be sitting here talking about going to Mars, and here we are. So it is all very exciting. So just tell me, though, exactly where are we as far as going? There's a lot that we know, but there's still a lot we don't know. Where are we on the slide rule of getting to Mars?
Well, indeed, with our orbiters and our rovers, we know an extensive amount about Mars. This actually helps Stan and the engineers here at JSC to really do a number of practical things in terms of the life support system, in terms of where they might go, what they might do, and the resources that they would need. But we're really just starting that process. I think as we get towards the end of this decade and certainly into the next decade, we're going to start using a variety of instruments and experiments that we put on the surface of Mars that would extract those resources. Now, a perfect example is a rover that we're putting together right now. It's designed to be launched in 2020. We'll sit on Mars in 2021, and it has one instrument that will bring in the carbon dioxide and separate the carbon from oxygen, separate and create the O2. So it's our first major step in being able to demonstrate that we could actually do this in a reliable way, and understanding when it might work the best. The huge swings in temperature on Mars. Does it work better during the day than the night? What about seasonal differences? All those things we can begin to collect data, and that will really aid the mission planners and be able to develop those systems that they can begin to rely on.
And do we have a landing site determined yet for the 2020 rover?
Actually, we're right now in the process of finding out where are the best places for the 2020 rover to go to.
Okay.
We started out with 100 sites where we took a good look at about 30 of them. Now we have about the top 9 or 10 of them for which we're acquiring much more data from our orbiting assets. And this data will be used to whittle that down to the top site over the next couple of years.
Can you describe what these areas of interest are, or somewhat like?
Well, one of the things that we want the 2020 rover to do is to core into the rock and then interrogate the hole, look at what's happened over time in that rock record. And then if we find something really exciting, we want to be able to cache the rock. You know, put it in a little sleeve and stick it in a container for potential return to Earth, where we can analyze it much more extensively, as I mentioned earlier. So we want to go to a geologically diverse site, an ancient site, a place that held a lot of water for long periods of time on Mars, a place where life could have existed if it started there at that time. And so there are many sites on Mars that give us that exciting opportunity, and the orbital assets will bring us back the data to help us make that decision.
And so do you have any questions for Stan? What do you need to know from him?
Well, what I want to know from him are the requirements in terms of those sites that we would both like to go to. It'd be great to find those sites that humans can live off the land to the extent of possible, and that's only going to, I think, increase in time as we begin to do more of those experiments. But also go to really interesting sites where we can do a lot of science. It's going to be geologically diverse. We're going to want water resources very close. Those water resources not only supporting humans, but also could tell us a lot about past life, tell us a lot about the amount of water that's existed on the planet in the past. So I think as we work more closely together in the future, we'll find those sites that overlap, that are both scientifically rich, but also those that would be really spectacular for humans to be able to set down, put in a base, and explore.
Mm-hmm. So to touch on a point that was made earlier, what do we need to know about Mars before we can send people there? We already know more about Mars than we did about the Moon when we sent astronauts there. So depending on how much risk you're willing to take, we can go. We know enough. For the requirements for a human landing, remember that at least at the first time we send people there, we're probably not going to send a mining team. We are therefore going to be bringing with us most of what we need. And if we use any local resources from Mars, it'll be resources from the atmosphere. So as long as the landing site touches the atmosphere, which I think doesn't rule very many of them out, we're good. Another thing from the human standpoint, of course, we're looking for a place that's relatively safe to land. The view from the rim of the Valles Marineris may be the most amazing spectacle in the solar system, but we'd like to land a few kilometers shy of it just so that we don't accidentally go off the edge when we land. So safe landing site, atmosphere, and beyond that, the reason we send people into space is that they're adaptable, and we could probably adapt our mission to any landing site on Mars. And again, if we do plan to use resources that are local to Mars on the first few missions, it's likely to be atmospheric, which is good anywhere.
So, landing on Mars and talking about the people, you know, you kind of touched on this. We need the people together. Can you explain, first of all, why it is that we want people? I think you touched a little on it when you talked about the rover, and it took, what, 2 years for Curiosity to move from point A to point B where it is today, at the same distance that maybe a human being could actually do in one day? Mm-hmm. Is that correct?
Exactly.
So can you elaborate more on why it's necessary for humans to go and explore?
Why don't you start?
Sure. Well, humans have the ability to make decisions in the field. That's far quicker than what we can do robotically. Right now, even though we are on Mars through our robots, they're really a distance away. And the light travel time from receiving information right on a rover and getting it back to Earth before we can even begin to make a decision can be anywhere from 4 minutes to 22 minutes. You know, that's the light distance from where Mars is and where the Earth is during those time periods. So we have to make decisions about what we want to do, and then we have to go back and tell the rover, okay, now we want to do this, or now we want to do that. And so they also have a limited dexterity, if you will. A human obviously could begin to chip away at a rock, see that he needs a different tool, be able to do that, be able to then look at it, and then make a decision, I want to keep that or I don't want to keep that, it has the information I want or it doesn't. And so all the dexterity and all the decision-making, real-time decision-making are so far superior than anything we currently have at Mars. It's just a huge step for us.
Very well.
So there's a great quote that I like to tell people, and this is from the leader of the Mars rover team, or one of the Mars rover teams, who has good reason to emphasize how good the rovers are. And he says that 1 day of rover operations on the surface of Mars is 1 minute of work for a human geologist. So what Jim said is absolutely right. A human in the field can do much more, scan the scene, see what the interesting thing is, go take a look at it, and that takes a long time to do with a robot. Now there is a caveat there. Every year the robots get better. Every year the people are about the same. So we're sort of in a race, and we'll see. By the time we get people there, the robots are likely to be far more capable. I'm not sure they'll be capable as a human geologist, you know, in the 2030s or when we're talking about sending people there. But they do get better each year, and that's something to keep in mind.
But perhaps if we're working together, side by side, robots and humans.
Oh, I think that's absolutely
kind of way,
how it has to go. I think to be able to support humans, to be able to be in a site and then take a sample and then stick it in a rover that's walking alongside of you and then analyze that and say, okay, that soil is okay, it doesn't produce carcinogens or something you take back into the hab. There's just going to be a variety of equipment and capability you're just going to want alongside you.
Yeah.
And I think having your pet rover, as I've called it sometimes, walking along and being able to provide some detailed analytical measurements is just going to make a world of difference.
It's totally fascinating, and I think that's about all the time that we have, but I really appreciate you guys coming out and talking with us. You can get more information going to the website at www.nasa.gov, and as always, continue enjoying the conversation on Twitter using the hashtag Journey to Mars. I appreciate you guys coming out. Thanks very much.
Oh, my pleasure.
You're
Thank
very
you for
welcome.